All right, great. Okay, welcome everyone for Space Cafe Tokyo May edition. And today we have a very interesting speaker and who happens to be a good friend of mine as well. Before we go to the speaker, let me actually introduce the Space Cafe a bit. So Space Cafe started about 2.5 years ago, and we usually have it in Tokyo at a really nice pub called Good Heavens Pub, where we invite either a scientist who's based in Tokyo or in Japan, or if we know someone who's visiting, we usually invite someone to come and give a public talk. And it's a really nice, cozy location. So in the future, if we go back, eventually when we go back, I invite those who are in Japan to join us. In the meantime, we are going to continue this online. And the Space Cafe team, I want to introduce. So it's Ken, who's online right now.
Hello.
And then we have Michael. And then we have Michelle and Ayako. And Ayako is also organizes the Space Cafe Japanese edition, and which also happens monthly. And then myself. So basically 5 of us are organizing this. And you can follow our all the updates on our social media networks, and then we'll update all the upcoming talks. And I also want to mention our venue host, the usual venue host, Good Heavens Pub, and they have been very gracious to give us a venue all these years. So even though we are not doing it at the venue, I just want to mention them that they're pretty solid place. So when we are able to go back, those who are in Tokyo, please drop by. It's in Shimokitazawa. And those who are joining through Zoom and those who are joining through YouTube, you can ask questions using the chat anytime, and we'll pick them up at the end, towards the end of the talk, and then Christian will answer these.
Oh.
Right, and then, okay, let me introduce Christian quickly before we go into the talk. Christian is currently based at University of Virginia. He's an astronomer studying exoplanets there, but he's Danish. He's from Denmark, and he's did his bachelor's and master's there, and then he moved to Leiden, where we actually met. And I remember Christian quite well because he's very keen on communicating what he studies, and he does his science with a lot of passion. And I've seen him doing outreach a lot. So it's really nice to have a scientist who's passionate about science and also actually communicating it with public, which is really important. That not only we do our science, but we also actually communicate with public, giving back to the taxpayers and so on. So today he will talk about these alien worlds that he's studying, exoplanets, what we can learn from it, and by studying, and how we can possibly detect life on one of these planets. So Christian, thank you so much for joining. Please let me close my screen, then you can start sharing your presentation.
Thank you, Celina, and konnichiwa, everyone. It is a real pleasure and honor to get the chance to speak with you all tonight. And tonight in Japan, it is 7 in the morning in Virginia, in the USA, where I live. But I'm happy to be up to hopefully entertain and fascinate you in the next hour or so. The topic of what I want to speak about is exoplanets, life in space, and how to find it. Who am I? My name is Christian Eistrup. I am born and raised in Denmark. And I did my initial university studies in Copenhagen, the capital of Denmark. Then I moved to Leiden University in the Netherlands to do a Ph.D. in astronomy, which I finished 2 years ago. And then I moved to the University of Virginia in the USA, where I am now an astronomy researcher. Aside from that, as Tilina already mentioned, I love engaging with people, speaking with people, fascinating them and entertaining them about astronomy. Also, one of my big passions in life, coffee, which is very necessary at this time of day for me. But if anyone has a drink of their own, cheers and welcome. My job is studying and understanding planets, which is a very fascinating job. And here I am at a conference presenting my research to my colleagues. But today I will take you on a journey into space. And like any journey into space, of course, it starts with our neighborhood in space, which is this little region here that we call our solar system. Maybe some of you have seen a picture like this before, maybe not, but I'm gonna go through what is actually seen here. To the left, the big orange yellow ball is our sun, which is almost rising now in Virginia. And moving out from the sun, we start with Mercury, Venus, our own Earth, and Mars, which are all these quite small planets that are quite close to the sun. They're all made of rock, cliffs, minerals. And because they were so close to the sun when they formed, they were not able to get as much material from around them onto them, because a lot of the material was warm gas heated up by the sun. And it's not until we get further away from the sun that we started to have more things that were cold, big blocks of ice that could start forming larger planets such as Jupiter, Saturn, Uranus, and Neptune. Now, 14 years ago, there was still an exoplanet called Pluto, but Pluto was changed, shall we say, into a dwarf planet in 2006 and is no longer considered a planet and included in this picture. So this is the solar system and the planets around the sun. Now, I usually ask my audience what your favorite planet is. But my favorite planet, or my answer to that question, is actually not in the solar system. My favorite planet is a planet called TRAPPIST-1G. It might seem a bit of a weird name, but the TRAPPIST is actually originating from a Belgian concept of Trappist monasteries that are brewing beer. And it's because this planet was found by a Belgian research team. And TRAPPIST-1G is a planet around another star than the sun. So my favorite planet is not in the solar system, it's outside of it. And in fact, there are billions and billions of stars in the universe. And like our own sun has planets around it, so do other stars as well have planets around them. This one called an exoplanet. with its host star there in the middle. This is not a real photograph. This is an artist's impression of how it might look in a foreign solar system. These planets can be, in fact, very close to their stars. There's a comparison here between a planetary system, that's the one at the top called Kepler 11, which has its star in the middle, and then it has 6 planets orbiting around it. Now, the interesting thing here is to compare how close those 6 planets are compared to our own solar system. Because in the same scale, we have our own solar system underneath it. And it turns out that the 6 planets in Kepler 11 are actually orbiting their star within the orbit of our own Venus. So they're very close to their star. And they can even be as close to the star as is the case with the TRAPPIST-1 system. The TRAPPIST-1 system actually has 7 planets orbiting around it. And you see that these 7 planets from the top are actually squeezing in to orbits very, very close inside the Mercury orbit in our own solar system. So these planets are indeed very close to their stars. So it looks like other planet systems are not like our own, which is an interesting takeaway. We sometimes think that we know how planetary systems are like because we live in one ourselves. So other systems might be like that. Turns out, no, they're not. And it also turns out that there are actually planets around most stars in the universe, or at least in our Milky Way. Astronomers estimate that there might be roughly 2.5 stars, 2.5 planets around every star in our Milky Way. And what you see here is an illustration. It also does work as a video where you see all these blobs dancing around in their circles. But this is a depiction of all the planets that have been found in the Milky Way galaxy. And each of these circles and circle systems is a planetary system with a star in the middle. And then depending on how many planets the star has, there are more or less circles around this central point. And then you can also see that the size of these blobs in the circles are bigger or smaller, indicating that we have a lot of different sizes of planets. So the planets that we can see out there are different sizes from our own solar system. There are different orbits from our own solar system. And the stars that they orbit around are also very different from the sun. So all in all, very much difference. So what do we call these planets around other stars than the sun? Well, I gave you a hint to the answer already. I wrote it once. We call them exoplanets. So why do we call them that? Well, exoplanets is a pretty cool name. It was a name that got my attention caught 13 years ago when I started getting into the field. I think exoplanets sounds pretty cool. But the reason it's called exoplanets relates from extrasolar planets, extrasolar. And what that means is planets orbiting around other stars than the sun. So there's only 8 planets in the Milky Way, because that's the 8 planets that we have inside our own solar system. Planets anywhere else are called exoplanets. So that does sound pretty cool, right? Now, today I will show you something about how planets form how we find them, what makes a planet habitable, and whether we can tell if something could live there, and what we're looking for when we look for life in space. And when I think we will find life in space. So with that, buckle up, and I hope you enjoy the ride. What I'm showing you here is a group of antennas. They're called radio antennas. It's a part of an observatory in Chile called the Atacama Large Millimeter and Submillimeter Array. It is located in the Atacama Desert, hence the name. And this long name is shortened down to ALMA. And ALMA is observing the universe at 15,000 feet, or about 5,000 meters altitude. But it observes microwaves, not visible light. And to give you an impression of what microwaves is, it's actually the electromagnetic waves that work inside your microwave oven if you heat up a dish or warm up your cup of coffee. The neat thing about microwaves is that they interact really well with water molecules, which is why they can warm up things that contain water. Now, this is a picture of my wife and I when we visited ALMA in 2017. As you see, it is really a desert. It is devoid of much life, except for all the people working up there. And it was, in fact, very, very cold, and we could barely breathe because there's only about half as much oxygen there to breathe as there is at sea level. And what that meant was actually that people said that if you get altitude sickness, the best cure for it is actually going down. But we were up there with a group. We had to wait for everyone to get ready. So in the meantime, my wife had to use an oxygen mask. And I felt like I was doing an intensive workout if I was just walking around slowly. So that tells you a bit of the conditions up there. Now, why would we actually be there? Why would the antennas be at a place that is so kind of hostile to life? Well, that is because this altitude is necessary, because we want as little of Earth's atmosphere as possible to interfere with the waves from outer space. So you can compare it a bit to the difference between observing the universe with a telescope in your backyard and then putting the telescope into space. We do put telescopes into space, but that's quite expensive. The benefit of space is there's no Earth atmosphere to interfere with anything. Whereas if you observe from your backyard, you'll get a lot of disturbance from the atmosphere. So the mountains and the high sides of the Earth are optimal for astronomical research. Now, what does ALMA see in the universe? One thing ALMA sees is star formation regions. This is a star forming, and here are possibly exoplanets forming around the stars in these rings and the gaps. What we see here is a planet-forming disk, and it was observed with the ALMA Observatory in 2014 and was the first real groundbreaking result from the ALMA Observatory, that we could see star formation and planet formation in action. What you see here is a young star that is called HL Tau, which has a disk around it of gas and dust. And the red and the orange features you can see in this image are the dust. So you can see that it's not just a plain smooth disk, it's a disk with some structure, rings and dark lanes, gaps. Now, this is a real image, but let's try and dive down into this disk and see what's going on there. So this is not a real image, but it's very beautiful nonetheless. If we get down into the disk, we see that there's a lot of solid objects moving around, what looks like rocks. And then you also see that the whole thing is quite diffuse or seems a bit opaque. So that's a mix of small solid bodies that we call dust grains and then gas. But we can have rocks floating around the sun. It works the same way as with our planets in the solar system orbiting around the sun. These rocks are attracted to the star here by the star's gravity. So the rocks float around in orbits around this star. Now, over time, these rocks can grow bigger and bigger by colliding with each other, and eventually also growing up so big as to form planets that you see have formed here. And you also see one of these solid bodies actually hitting the planet. Now, there's nothing actually dramatic about that. It's simply a matter of two solid bodies colliding with each other. And then the result of that is that they kind of merge. And the masses and the materials that they have all go into building this planet bigger. And then when we have a planet formed, then the planet gets an atmosphere, just like this beautiful blue layer around the Earth. So far, so good. We've formed a planet. Now, how do we actually find exoplanets? Generally, we have used big and powerful telescope, like the Hubble Space Telescope, which has been operating in space for 30 years. It's a NASA telescope. And then also the Very Large Telescope, the VLT, in Chile, operated by the European Space Organization. So Hubble is by NASA, and VLT is by ESO, the European Southern Observatories. Both these places, both these facilities are really powerful, very big telescopes that are capable of really detecting the faintest glimpses of light from space. But the way that they observe exoplanets, what they can do, you can actually imagine. And I've only experimented with what I'm going to do now when I'm in person with an audience, but I'm going to test it out with all of you who are listening now. Because I want you to close your eyes and let me take you on a journey. And I will let you know when I want you to open your eyes again. Now, imagine that you are outside. It is a clear sky night and you find yourself on a nice grassy field. You brought a blanket with you and you put the blanket down on the grass and you lie down on the blanket staring into the sky. You have deliberately left your phone back home and your laptop back home, and you are in a place where there are no streetlights and there are no houses around that have lights on. So the only light that you see is the little bit of light that's coming out of the sky from the stars. So you lie down there on your blanket and you stare into the sky, and little by little your eyes adjust and adapt to this light coming in, adapt to actually looking at the stars, taking in the light. Now, you find a star, one specific star that you want to focus on. And you keep staring at that star really intently, trying to familiarize yourself with it, really getting to know the star. Is it a bright star? Is it a faint star? Now imagine that the star has an exoplanet moving around it. And sometimes this exoplanet is next to the star, as seen from you. Sometimes it is in front of the star, and sometimes it's behind the star. But what happens to the light that you see when the exoplanet passes in front of the star? And that is when I wanted to open your eyes again. Because the star actually became dimmer when the exoplanet was in front. And this phenomenon is what astronomers call the transit method. Now, down here you see a measurement of the star's brightness over time. And look at what happens to the star's brightness when you see this planet moving in front of the star. The star's brightness decreased a little bit because the planet was blocking some of the light. This effect is exactly what astronomers are looking at when they are finding planets, finding exoplanets. And in fact, this transit method, quite logical as it actually is, that light is simply being blocked by an exoplanet, has been used to find thousands of exoplanets by now. But sure, exoplanets and planets are interesting, or it's fascinating that we can find them, but why are they actually interesting? Well, one of the big questions and the big reasons and motivations for going in this is because we want to understand our place in the universe. And so we ask, could there be life on other planets? Now, first of all, before actually talking about life on a planet, we kind of need to know what makes for a planet to have life on it, what makes it habitable. The Earth is habitable because we are on it, but what aspects of the Earth is it actually that makes it habitable? What is needed for life? Now, the Earth is habitable because we obviously live here. Some of the things that make it habitable is liquid water, the air and the air in the atmosphere. And the combination of the environment we're in, the place around the sun we're in, is actually what causes this. Now, to the right here, we see all the 8 planets that we know, and we see here in the middle, vertically, the sun. But if we go to bigger stars with more light coming from them, then we see that this green belt that runs through the Earth is actually moved a little bit outwards. This green belt is, generally speaking, what we call the habitable zone. The habitable zone is the region around a star where a planet has just the right temperature to have liquid water. And if we go to smaller stars with less light, we see that this region moves closer to the star. And when we have a bigger star, the region moves away from the star. And that's logical because a bigger star with more light will heat the surroundings more. So the right temperature space will be further away. And vice versa, if you have a small faint star, you will have the right temperature closer to this star. Now, I showed you this image, this illustration of TRAPPIST-1 earlier. What I didn't tell you about was actually these colors, because the artist here has neatly colored the regions that each of these planets is orbiting in. So you see at the top part that there are the planets B, C, and D that are orbiting in a reddish area. Red here is associated with fire and heat. So this is an area where we don't expect liquid water to be present. It's too warm. Then we have E, F, and G that are orbiting in this green region, which we assume to be the liquid water region, the habitable zone. Then we have the planet H, all the way out there in the blue region, blue here representing coldness. So this is where water would be in the ice phase. And there we have my favorite planet, TRAPPIST-1G, conveniently orbiting in the habitable zone. To be habitable, a planet needs the right temperature, but also the right size. And the size comes from having the right atmosphere to be made of rock, like the Earth. So if your planet is too large, say like Jupiter, for example, then there will actually be too much atmosphere on it. Jupiter's atmosphere is several thousand kilometers thick, and that's too much for life. But on the other hand, if you have a small rocky ball that's not quite as big as the Earth, it might not actually be able to hold on to any atmosphere. And the atmosphere is important because that's where the air that we breathe is in. And the atmosphere is what regulates an exchange between the oxygen that plants, for example, breathe out, that we breathe in, and the CO2 that we breathe out that plants can use off. So it's a part of sustaining the whole ecosystem of the Earth. Now, the sizes of the TRAPPIST planets, therefore, is also interesting and important. And with the size comparison here between the solar system on the lower and the TRAPPIST-1 system on the top, we see that the TRAPPIST-1 planets generally are quite similar to the solar system planets. In fact, the TRAPPIST-1G, that's the green planet, second to last, is actually quite similar in size to the Earth. So the size might be good for sustaining life. Now, if any of you have questions about the structures of these planets, because there seems to be red dots on TRAPPIST-1b and TRAPPIST-1G seems to be green and so on. These are not observed features. We have not got that much information about these planets yet. So it is an artist's impression. A viewer has gotten an impression and tried to draw structure onto the planets, but it's not how they physically look. We don't know that about them. So first, planets, then habitability. How about life? How do we actually find it? Well, the only place we know that life exists is on the Earth, because we have plants and we have life here. And humans, for that matter, and animals. But what are we actually looking for when we look for life in space? We are looking for something that we call biosignatures. Wait, what? That's a weird word. Signatures of biology. Signs of life. We might as well say signs of life. In astronomy, the biosignatures is the fancy scientific term. What we mean is signs of life. Yay. And these signs of life are still mainly oxygen, O2. We have O2 in the Earth's atmosphere, and that is why we can breathe as humans, and that's why we can live. So since we don't know about any other forms of life that could inhabit a planet, then what we're looking for is still life that looks like us, and that would be dependent on oxygen in the atmosphere. And the way we see oxygen in an atmosphere, or expect to do it at least, is this. When the planet passes in front of the star, now imagine that the observer is on the right-hand side, where the arrows point to. If the planet passes in front of the star, there's some light from the star that gets blocked by the planet itself. But you see, there's also a small bit of starlight that passes through the planet's blue atmosphere. And depending on what is in this atmosphere, this light will be affected by that. So if there are water molecules or CO2 molecules, or maybe even O2 molecules, these molecules will affect the light that is passing through. And what will happen is that we as an observer can see the small changes that are made to the starlight. And we can analyze these changes and deduce what molecules caused them. So we can actually look at a star, have a planet move in front, analyze the light coming through its atmosphere, and tell something about the composition of the atmosphere. And this light, therefore, will show what is in the atmosphere of the planet. And if there is oxygen in it, then we will have found life, is my claim. What I think will happen is that the research team who finds it will claim that they found life. And then we can begin a discussion afterwards regarding whether this is a sure detection of life or whether there could be other reasons why there might be oxygen in the atmosphere. However, to see oxygen in an atmosphere like the Earth's, we need better telescopes than we have now. Even, as I mentioned, the Leiden Observatory, the VLT, and the Hubble Space Telescope. They have all been pushed quite far with their capabilities, and especially Hubble and VLT are not powerful enough for it. So we need better telescopes. One of them that will come into use in a few years will be the Extremely Large Telescope. Now, you see, astronomers are very creative. We name a new big telescope the Very Large Telescope 30 years ago, and then we want to build something bigger than the Very Large Telescope, so we call it the Extremely Large Telescope. And in fact, there was an idea for constructing the Overwhelmingly Large Telescope that got cut off. But the Extremely Large Telescope is also going to be built in Chile, and it will be 39 meters in diameter, where the largest current telescope is 11 meters. So that's almost 4 times as big radius, maybe 20, 30 times as powerful. You can see here the small dots next to the telescope building are cars. So that's for scale comparison. This is going to be a big, very powerful new eye on the sky. But ground-based astronomy, so that is facilities that are located on the ground, is not the only things that are going to happen. We are also going to soon replace the Hubble Space Telescope with the James Webb Space Telescope. And just for clarity, this is the part that is Hubble Space Telescope. The part underneath is simply drawn for comparison with a human size. And likewise with the James Webb, this is the part that's actually going up. But the humans down here give a size comparison. So the Hubble Space Telescope had a mirror diameter of 2.4 meters. But the James Webb Telescope will have a mirror diameter of 6.5, which in turn means that it will be 7 times more powerful. And I know 6.5 is not 7 times 2.4, but it's about the area that they have on. 7 times more powerful than Hubble. And that means that it'll be able to look deeper into space, see more detail on things in space than we have ever seen before. But Hubble is orbiting around the Earth all the time, and Hubble has been repaired and upgraded by astronauts and space missions throughout its 30-year lifetime. JWST, the James Webb Space Telescope, will not be the same. The James Webb Telescope will not orbit close to the Earth, and it will not be serviceable. We will not be able to go there. And I'm going to show you now a video of how it's going to get to where it's going. It's a 29 nail-biting day journey, but I've cut it down to 2.5 minutes. That is quite a journey. It's quite an undertaking to get everything unfolded. But what makes it even more nail-biting is that if anything in this sequence goes wrong, there's no way to fix it. We cannot go to the James Webb Space Telescope. It will be lost. The reason we have to do all these things is because the James Webb Telescope is so big that it does not fit into an ordinary spacecraft that we can send into space. So we need to fold it all together, send it into space, and then unfold it. And you see how, and you saw how many things had to be turned and unfolded and stretched before everything was ready. It's a long, difficult sequence, and we cross our fingers that it goes as planned. But if it works, we will have a new eye looking into space. And with that, these new super space telescopes will start observing in 5 to 10 years' time. So stay tuned, and I think we will discover soon that we are not alone. And with that, arigato gozaimasu.
Right. Thanks, Christian. It's quite the journey actually you took us. So there are two questions, and that I saw on Twitter, and Ken and Michael will look for other questions as well. But let me start with this one quite interesting, something I have been wondering when I saw it. It's from someone called Nega. Hopefully I'm pronouncing these names properly. So this person is asking, do you have to build bigger telescopes to see far, or isn't there other technological way to do it? For an example, our computers became smaller and lighter, but super powerful. Why do you need to build bigger to see far?
That is a very good point. Because indeed, technology improves. So why do we need to build bigger to see far? There are a few aspects to it. One of them is that in addition to just having a certain size of a telescope, giving how accurate and sensitive that telescope is, there's also been development of several supporting techniques to existing telescopes. And when I say supporting techniques, I mean astronomers have built lasers that are shot off into the atmosphere from an observatory. And this laser can analyze the movement and the shape of the atmosphere above the telescope, such that the atmospheric interference can be corrected for in the observations. So that's one way that we are aiding existing facilities. But one of the big things in astronomy with regards to the size is that the bigger the size of the telescope, the more light this telescope can collect. It's simply a matter of saying, if you have a small mirror, then you can only collect as much light as hit on that mirror. But if the mirror is 100 times larger, then you can collect 100 times more light. And the shorter time you can collect that light in, the less risk you have of too much of this light being interrupted by atmospheric effects and so. But it's a constant balance between taking the size that we have and improving the precision by accounting for things around the telescope, and then actually building the telescope larger. So it's a big joint venture between improving what we have and building something new. But I hope that was an answer to Mika's question. Otherwise, Mika, I'll be happy if you reach out to me. Yeah.
Great, thanks. Let's take a question from the Zoom. Yuki Kubo. Before the question, Yuki says, "Nice tie," by the way.
Thank you.
So I'm glad people noticed. Yuki is asking, what is the main advantage for constructing one single extreme large telescope, not VLBI interferometer on ground? So what's either doing like one single large telescope or maybe several different smaller ones like VLBI?
So the VLBI is an interferometer system. And so the VLBI and the VLTI are two different things, but they are using the same techniques, but in different wavelengths. A main motivation for using one big facility rather than interferometry is that if you're using interferometry, you need to combine the signal from different telescopes. And while this can sound like you just take the cables and put them together and combine the signal, it's not as straightforward as that. If you have one big dish, one big mirror, it's easier to handle the signal coming into that mirror itself than to handle the signals coming into different mirrors that are combined. That's not saying that you cannot do that, because we are doing that, but it's hedging our bets in different directions such that we get the maximum out of what we have. Again, if what was the name of the person?
Yuki.
If Yuki wants more information about it, I'll be happy to have it extra.
Okay, great. Let's take a question from YouTube. Eric Nyman is asking, could you tell us something about the composition of the surface of a planet in terms of habitability? Is this composition influenced by size or distance?
Thank you, Eric. We don't know exactly how these planet surfaces might look, except for the things that we've been able to derive with regards to the mass and their size, and hence their density. So we can say something generally about the density of planets, and we can roughly put them in categories at this point, whether the planets are made of say water ice, just like a big snowball, whether it is made of minerals or rock, or whether it's just one big clump of iron. So we can distinguish roughly between those three phases. That said, with the sensitivity we have now, it's sometimes unclear where we are, because the error bars that we receive are a bit too large to constrain them precisely. Now, what would we expect for a habitable planet? Well, what we know about the Earth is that we need a surface, we need temperature, and we need water, and we need an energy source. So we expect that if the planet should be habitable, we need some water on the planet. It's simply a solvent in all biology that we are used to here. So we need a surface, we need water, and we need an energy source. And whether that energy source is the sun or whether it's chemical energy from foods, that is what we will be looking for if we are looking for the life.
Nice.
And Eric, if you want any more information, be happy to reach out.
We have a question from Shogo Kobayashi. Kobayashi-san says, thanks for the nice talk. And the question is, in terms of finding biosignatures or maybe oxygen, what type of star do you think that will be most suitable to find them?
Thank you for the question. I'm personally not completely sure what the answer should be to that question, or what the answer is to that question. The reason I say that is because the oxygen element to a biosignature is a signature that we are used to from the Earth. But the solar system style, as I've shown you, is not a common style of planetary system as we see. Much more common is to see stars that are smaller than the sun, what we call M dwarfs, smaller and fainter than the sun, that have planets around them. And these planets could likely be habitable. But then in turn, whether the oxygen signature is the biosignature that we might be able to observe from these is a different question. So I'm actually not sure if we should look at the smaller, fainter stars with planets around them that are more common than the sun, or we should aim at sun-like stars. It's probably a matter of hedging our bets and going for observing both types.
Right, nice. I'm going to take a question from Twitter. Saito-san is asking, can all these big telescopes observe exoplanets?
The short answer is yes. All the telescopes that I've shown in this presentation can observe exoplanets in one way or the other. Yes.
Great. All right. Let's take a question from YouTube. Saralyn Campbell says, "Arigato to you for the talk." And the question is, what is it about TRAPPIST-1G that you love or find particularly interesting?
I think a thing that I got sort of attached to about that planet was that the planet was discovered during my PhD, and it was discovered as a part of a planet system with 7 planets. So it was suddenly a system of planets that looked to some extent more and more like what we have in our solar system. I know that there are several efforts with the James Webb Space Telescope's so-called guaranteed observations. So the James Webb Telescope has not been sent up yet, but certain observational programs have already been accepted for the James Webb Space Telescope. And those programs include investigations of the TRAPPIST-1 system and TRAPPIST-1G. So it's also a matter of where, like maybe a planet that, an exoplanet that I hope or expect that we will relatively soon know much more about. So that was what got me excited.
All right, great. So a freshman from a Japanese university, Taro Tanaka, is asking a question that Taro-san says, I heard a project of building telescope between other planets in solar system. In the future, are we able to do such a project? So I assume Taro-san is asking about building a telescope maybe in other planets in the solar system.
We're generally able to do what we put our minds to do with regards to technology. Yes, there are plans to put more telescopes into space, not just into space, onto other planets. Obviously, it is super expensive. And the thing that we would get out of it mostly would not necessarily be to just have a single isolated observatory on Mars or something. It would be the capability of those telescopes to work together with telescopes on the Earth and combine their signals to achieve greater sensitivity and look deeper. The problem with that is that the further we get the telescopes away from each other, the more difficult it becomes to combine their signals. So while I don't think it's a bad idea, it's probably just not going to happen very soon. But who knows, maybe within 30, 50 years.
All right, so let me pick the last question for today. Kohashi san is asking, what do you think about Starlink? So Hashi-san says, I think it disturbs observing stars.
Yeah, thank you for that question. I was about Starlink. I was actually outside my house here about 2 or 3 weeks ago when the first Starlink almost train across the sky of satellites appeared first, and it looked completely surreal to me. The Starlink is not beneficial for astronomical observations. It's not. It is going to disturb astronomical observations, and I can be sort of annoyed at that fact that it'll be more difficult to do astronomy. On the other hand, astronomy is not necessarily only a science or the only field that has access to space or that should necessarily get sole access to the space. And it's not me taking an opinion on it, but I'm aware that there are other uses of space. For example, the Starlink providing internet to more people on the Earth. And I'm aware that that is maybe a higher priority for some people than astronomy is. So I don't think that we are going to get rid of Starlink, and I probably expect that more things like Starlink will come up, which will, in one way or the other, disturb astronomy. But astronomy will have to keep going and fight its way for as clear skies as we can get for observations.
Yeah, I agree. Even though I said that's the last question, let me actually give you one more question. So this is the last question. Shogo Kobayashi-san is asking, finding exoplanets, especially rocky planets, seems to require a great amount of luck because a system should have high inclination angle. Is there any other effective method to find such tiny planets?
So that's a really good question. There are several ways of finding exoplanets. The transit method is probably the most intuitive one because it's simply star dimming by a planet. There are other methods. One of them is that we can measure the gravitational pull on a star from an exoplanet by seeing the star wobble on the sky. We can measure that. But that signal is bigger if the pulling exoplanets is bigger. And if we go to the rocky exoplanets, they are smaller. Generally, it is probably the transit method that we will go for when looking for smaller rocky exoplanets. Although there is a method such as what's called gravitational microlensing. And that sounds very complicated. And it was a method pioneered the idea by Albert Einstein. But microlensing is actually saying that no matter how big or small a planet is, under certain circumstances, we will always see it. But it is a little bit more of a lucky shot observation than transit. So if we look at a transit star and planet, we will keep seeing the planet going around the star all the time. We know it will. But with microlensing, although microlensing can see smaller planets, we don't know if we will be able to see it. It's a bit of a lucky shot situation. To get back to your question, thank you for your question. I think finding smaller rocky exoplanets will be a matter of taking, especially the transit method, and improving the sensitivity that we have on that.
Excellent. Right. Thank you so much, Christian, for your talk and answering all these questions. And I really hope that you will be able to visit Japan at some point and give us another lecture in the future in person. And, yeah.
It is very high on my list. I want to get to Japan and I want to see everyone in person.
Excellent. And I also want to thank everyone who joined on YouTube and Zoom and asking so many questions on YouTube and Zoom and also on Twitter. And before we leave for tonight, or rather today, I have a couple of announcements I want to make. And as you know, we usually meet in person in Shimokitazawa at Good Heavens Pub. And in order to support the venue and also to Tokyo Space Cafe, we charge a very small amount of an entrance fee. But these online versions, we don't do take any charges. But we would like to encourage everyone to contribute to a program. And we have been wondering what kind of program we should promote where you can help that would make a difference. And so the International Astronomical Union announced this, today they announced this program where people can donate a small amount, and that would actually be useful to contribute to an astronomy program around the world, which are especially affected by COVID, and that could have a societal change. So in your screen right now, you can see the URL. It's iau.org /donate. So if you go there, you can donate. And then I want to mention that we will meet again next month online. We are definitely, at least for next couple of months, we'll meet online, and we'll keep you posted of the next meeting and announce the lecture and the topic in the coming week. So please follow our social media. And I want Ken and Maiko to come online just to say hi and bye for everyone. And again, Christian, thank you so much for, first of all, waking really early in the morning at 7 to give this talk at 7 a.m. in your time. And thanks everyone else who joined in today. So it's, I'm Tilina, and then we have Maiko and Ken. So all the organizers are signing off from Tokyo. Thanks. See you next month.
It's a pleasure. Arigato gozaimasu, everyone.
Thank you, Christian.